maybe my book or a few other things. So it's kind of fun for me to be here, and I'm not sure if Professor Yang Guang said that I'm going to be here for 3 years, kind of a few weeks at a time. And it's fun for me because slowly I'm beginning to pick up a little bit of Chinese. Maybe in the very end, 3 years from now, I will give my last talk in Chinese. So let's see if this works okay here for going forward. Oh, yes, there we go. Okay, so first I apologize. Maybe I might embarrass a few of you here in the audience because I have really been treated very well here. And so I want to thank a number of people who have kind of taken care of me while I'm here. And I've had an opportunity to visit part of Shanghai in China. I've spent time in many places in China, from Shenyang to Xi'an to Zhengzhou, and mostly in Shanghai. I've had an opportunity to see Zhujiajiao, and that was thanks to Jiang Caihang, who took me on a trip there. And then while I was here, I got a chance to visit Yu Yangguang. Is that right? How do you say that? Gongyuan. Yuyuan. Yuyuan, yes. So I had a chance to go there. That was very nice to see a little bit of Yu Gardens. And then this young lady's really spoiled me, but she's working downstairs right now, collecting rat data. And interestingly, doing this rat data on iron particulates. So it's kind of interesting. The last few slides I showed today, maybe she'll actually be able to demonstrate some of that for you right here at ECNU by the time she's done those experiments. And Yang Guang has really welcomed me here and given me an opportunity to meet many of you and to discuss a number of interesting projects. So while I'm here, please feel free to talk to me if you have questions or interests, and I'm certainly easily available when I'm here. So I'm just going to give you a little bit of history because, you know, it's one thing to see me today. The question is, I was as young as you one day, a long time ago, and I was just as excited then as I am today about what we're doing in MRI. So this is me with a good friend of mine. We started to do MR back in 1983. And this was a very interesting time period because they had just finished kind of the early development of resistive magnets. So imaging at 0.15 Tesla. In fact, historically, there was a magnet called an instrumentarium magnet at 0.1 Tesla, a very low field, that actually gave the best images of the lungs I have seen in 30 years. And you might ask yourself, why? Now, you're still doing low field, is that right? And what field strength are you using? 0.35. 0.35. Okay, so 0.35 became very common with Diasonics about 30 years ago. So when Diasonics began its business, it jumped from 0.1 to 0.35, and they thought that's a really big increase in field strength, right? 3.5 times higher field strength meant 3.5 times better signal to noise. So in those days, this was really great. But what if I told you, Yang Guang, that in fact, maybe imaging at low field has big advantages over high field, especially for your project? Strange, eh? How is it that low field can give us such good results? Well, one of the reasons we have to remember is when we go to high field, we also have very high changes in local magnetic field. These dipole changes come about because of the presence of iron in the tissue, because of air in the tissue, and they have very bad effects. And in the lungs, of course, we have lots of air, way too much. The problem is we only have about 10% water content, whereas in the rest of the brain, we have about 80% water content. So 8 times better signal to noise right there compared to the lungs. However, at low fields, those dipole effects aren't so big. So in fact, at 0.1 Tesla, you see the lungs much better than at 1.5 Tesla. So something to think about. And when we talk a little bit about a new technique called QSM, I'm going to suggest that there's a project we could do, young one. We could collect the phase data from low field, so if you can get me this data, and we can actually image bones and air at low field, because the susceptibility effect of bones and air is something like 50 to 100 times bigger than in the rest of your body. And therefore, I don't need these high field strengths. I can go to a field strength 50 times smaller and do a good job. So in this case, we're not 50 times smaller, we're 10 times smaller. So actually, I should be in the perfect world of creating a whole new way to maybe image lungs of Chinese people. Because in China, sometimes your air is not so good. And so you can cough a lot, you can get lung problems. And maybe the presence of low field would be a new way to image lung disease in China. So I think there's some interesting possibilities here. Anyways, at that time period, everything was new in MR. So for me, I started looking at something called segmented echoplanar imaging. And that is a method that is very fast. It's come and gone over 30 years. People are just reinventing it again today, 30 years later, so this makes me smile. We did 3D cardiac imaging. We did what's called multi-point water-fat-Dixon technique, which has become very popular here 30 years later. We did in vivo motion tracking, and we did image reconstruction from non-uniform sampling. All this done in 1985, 1984, 1985 time period. So, you know, people had the same ideas you do today. We just didn't have the technology you do today. We didn't have the fast computers. Oh my heavens, I'll tell you this cute story. I remember one day we bought this big disc. It was like this big. It cost me $2,000 then. 10,000 RMB. Today, imagine in today's dollars, that's like, you know, maybe the equivalent of 50,000 RMB. And you know how much it held? 200 megabytes. So that was enough data to start storing data for me back in those days. The gradient strength that we had on our magnets was only 3 millitesla per meter. Today you have 50 millitesla per meter. Everything you have is dramatically better. But that didn't change the fact that we still had the same ideas at that point. It just means you can do them better today. Oops. So in 1985, so I only spent 2 years at Picker. Picker International was one of the early companies that built superconducting magnets in that time period. And in 1985, I then went to Case Western Reserve University, a place called University Hospitals. And this is when we first invented MR angiography, so the concept of flow compensation. This was when we first did super resolution imaging, where the Fourier transform theory can be completely eliminated. The concept of a pixel, you know, when somebody talks about imaging with a certain resolution, if you collect an object that is, say, my brain with 256 millimeters, using 256 points, then I have 1 millimeter resolution, right? But actually, I'm telling you, you can design the mathematics of this that even with 64 points, I can give you infinite resolution. It has nothing to do with the limits of Fourier theory. So sometimes what you learn in school can actually be very restrictive on your thinking. And I will tell you a cute story about a very well-known guy. His name is Zhipei Liang. Maybe you know him. Liang Zhipei. He worked with Paul Lauterbur for many years, but he was my PhD student. And recently he helped start the Lauterbur Imaging Center in Shenzhen. And he's very well known both in the United States, I think, and in China. But a cute story is he came into my office one day just when I was developing this super resolution theory. And I started to explain to him on the blackboard, okay, what this concept was, and that Gibbs ringing no longer mattered, that you could do this infinite resolution. And as I started talking, he got more and more upset. He says, oh, this is not possible. I didn't learn this in China. This is not what signal processing tells me. And he literally ran out of my office. It was like, he was Lao Shi. He was like a scared mouse. He just disappeared. And I thought, okay, I'll wait till the next student comes. And maybe I had a bad reputation in those days of being very tough. And anyways, a few days later, there's a little knock on my door. And he says, He says, well, you know, actually, he became very famous because of this project. So the fact that he was able to you know, get through the wall, to pass through what he had originally learned and realize there were other ways to do things, then he really made a lot of progress. So it's very important, of course, to understand the basics of what you do so well that you can also understand how to overcome some of the limitations of what you do. So what else did we do at that point? I wrote a paper then called about electric tissue properties. This was actually just a one-dimensional solution of how to extract the permittivity and conductivity from an MR experiment. So if you're a material science person, you want to study that type of electromagnetic property, right? Well, this is funny because this paper sat there for almost 20 years. Nobody quoted it. I looked for fun on what's it called, Google Scholar. And if you look at the number of number of quotations of this paper, it's like 1, 1, 1, and then 20 years later, whoosh, it goes like this. And why is that? Well, that's because at Highfield, people could now do three-dimensional electric tissue properties. And of course, just coincidentally, we published the basic idea in that paper 20 years ago. So you never know, just hang on, whatever work you do today, maybe 20 years later, people will realize that it's interesting, right? Okay, at that point, I stayed in Cleveland for about 15 years, and then I went to St. Louis, to a place called the Mallinckrodt Institute of Radiology. That was at Washington University in St. Louis. And there we began looking at functional brain imaging and the basic concepts behind it. And this is really when I started to look at the fact that the venous system carried deoxyhemoglobin. And this made us start to look at iron content in the brain. So right about that time period, 1994, 1995, I was working with a fellow named Z.H. Cho from Korea. So he's also a very famous early pioneer. And interestingly, actually, it was about 1986, we ran one of the first MR meetings in China. So here was an American and a Korean coming together to run an MR workshop in Beijing. And this was very interesting. We had an audience pretty much like today. Most of them were physicists or engineers. A few of them were radiologists. And at that time, things were so difficult in China that one of the biggest requests that we got was to send journals to China. Boy, have things ever changed, right? You just get on the internet today, pop in exactly what paper you want, and you're flying. So you have to realize that in your generation, you're so much luckier. You can accomplish so much more than your parents could, or your parents in the sense of the previous MR generation. So that was a lot of interesting experience for us. So this concept of functional brain imaging is all based on the presence of iron. It's based on the change of deoxyhemoglobin. But at that point with Z.H. Cho, we then started to look at iron in the rest of the brain. And in fact, some of the first phase images that were published with amazingly long echo times, I believe 120 milliseconds at 1.5 Tesla. So that's like 60 milliseconds at 3 Tesla. You will find those published in an IEEE journal back in 1995, where we began looking at that phase behavior. So we then started to ask, can we get rid of background field inhomogeneities? And when we started to realize we could remove a lot of the air tissue interface, we then came up with something really fantastic, and I'll show you when we get to that technical part. But when we removed the background phase, all of a sudden, the brain came to life. We could see things we had never seen before. And for 10 years, for the first 10 years, maybe even the first 20 years of MR, people just threw this information away. In fact, so I have to tell you another quick story here, because this is really important for you. Almost every new development in MRI has come from a problem. So for example, getting rid of the air tissue interface led to the concept of QSM, of quantitative susceptibility mapping. Getting rid of T2 star effects led to the study of functional brain imaging. Getting rid of the artifacts from flow in the brain. When I first tried to look at flow, in the brain and in the heart. There was nothing there on the MR picture. It was completely black. And until we created this capability to refocus moving spins, we never saw blood. So the first problem I was given when I was your age, when I went to this company, Picker, was, we have all these terrible artifacts. Can you fix this? Well, that was my first challenge. It took me 2 years to solve that problem. But once we solved it, all of a sudden, we didn't just get rid of the problem. Now everybody could image blood vessels. So every time you have a problem, maybe it ends up leading to something totally new. And in the case of the air tissue interface, at the end of my lecture, if I ever get there today, maybe we have to have a second lecture, young one, because it's taking me a long time to tell you all these stories, I'm afraid. But I think probably worth it. Anyways, if I get to the end of the lecture, you're going to see that this ability to remove air tissue interface can now open a whole new door to imaging materials. I'm actually going to show you that I could image this phone and everything inside it, even though there's no protons in this phone. So that's pretty amazing, because you would think I have to have protons to be able to image something, right? All of these things lead to new ideas. So in 2002, I went to Wayne State University in Duluth, in Detroit, Michigan, and we set up a group of people. It took me a few years to set this group of people up. We have about now 35 people doing MR in Detroit. And we have students who come from mathematics, from physics, from biomedical engineering, from chemistry. It's really a wonderful mix of students who come together. But sometimes the most important people who join our group are actually radiologists, because we kind of know what we want to do from a technical point of view. But sometimes if you have a radiologist sitting beside you, they're going to tell you, that's important, that's not important. Or you didn't really discover the correct function of this part of the brain, maybe the pituitary gland, for example, where you want to study growth hormones. You don't have a radiologist there, you may miss a lot. So they play a very important part of your learning process, because since a lot of what we do is medically oriented, we shouldn't be so stuck that the only thing we do is mathematics or physics or chemistry. We should try to learn as much about physiology as we can in our processes. And then I think he mentioned that we have published this book. The book actually just came out again. So this summer, the second edition of the book is available, and it has new material in it, has parallel imaging in it, and a number of other things. And I would say I have been lucky enough over the years to have almost 100 students. And many of these students, they're now working in industry. Many of them are at universities. People like Dubiao Li, Wei Li Lin, many Chinese students are among that group of people. And I'm very proud of them that they have gone on and developed their own academic programs. And probably at this point, I'm a grandparent, maybe even a great-grandparent, as they have got their own students and their students have got students. So one of the things that I want to close this introductory material with is, so at this point, for me, I've had a lot of fun in MR. Obviously, you can tell we've done a lot of things over 30 years. And so the question is, where are we today? And where can we go tomorrow? So for me, I have that flexibility at this point in my career to not have to focus so tightly like you do on your projects, where you have to get that project done, get your PhD, and get out into the real world. I want to ask new questions. And here are 5 of these questions. So first thing is, in my university, we tried to develop what we called a dual title program. And so we all have the same departments, math, physics, chemistry, etc. But many of you do imaging. So we tried to create a new program where we could take all the imaging-related courses at the university and give the students a dual title. So this way they get a degree in imaging, in mathematics and imaging, or physics and imaging, even neuroscience and imaging, right? Or chemistry and imaging. English and imaging would be tough. But it's not impossible if you do fMRI, so it depends how good you are at mathematics, right? So this is something we have created. So anyways, at the end of this, you can come and check this out if you want. The MRIMidnightClub.com.
Oh, midnight. Sorry.
Okay. No, that didn't come out right. All right, so the next thing we would like to do is to maybe have a more international forum where, you guys, if you have questions or problems, you're trying to overcome something in your research, that you have a place to post this. There are many people, for example, who are looking at doing iron tagging of proteins, for example. There are many people who are doing compressed sensing, for example. What we really need is a forum of the unanswered questions and how to tackle certain problems. And one of the stories I wanted to mention to you guys is that in the old days, most places would just do research within their own group. That's all. They didn't want to talk to other people. They don't want to collaborate with other people. That's still a big problem today. But to give you a simple example, in the United States, when I write a grant, to get grant funding for us is very hard today. If 1,000 grants are written, in the end, only 50 of those will get any money. 1 in 20. So if you were to study compressed sensing and you wrote a good grant, the odds are you're not going to get money for it. And maybe 5 other sites in China, they might all be doing this. So the people in Shenzhen, they have a big group doing compressed sensing. In Beijing, nobody's going to get the money. But if you work together on this and submit a grant as a group, you may have a much better opportunity to get funding. And of course, to make much more rapid progress in what you're doing as well. So I am a very strong advocate of what is called team science. Working together to get things done faster. And I think the internet is making that more and more possible. Now, another thing I would like to do is to have a lot of the talks that are given in individual universities. Sometimes you guys give some really great talks. Maybe the students give special presentations internally. Why can't we have a library of these presentations where people could go and listen to this, especially on the educational side? Something else that I would like to see happen. And then finally, what are some future projects? What are some future directions? In my case, I'm just converting all my papers to PDF files. So over the years, I have collected thousands of different papers. And finally, about 6 months ago, I began sorting them out. And my wife was very unhappy because every room in my house had, here's 1,000 papers in this room and another 1,000 papers in this room, but finally organized according to topic and area of interest. So in order for me to help start that process, I'm going to go and take each of these and create a list of maybe 100 or 200 unanswered problems in MRI. Where can you as a student go to find something critical that you can answer as part of your study? So this is also something I would like to do over the next maybe 3 years. All right, so now we're going to switch gears and let's get into some technical things about MRI. So in MR, of course, we want to do a very good job for the physicians. We want to collect the data quickly. We want to do imaging that has great contrast so they can see all the structures in the brain. And of course, we want to make sure that the data that we're showing them represents the true brain itself, right? Because if we show them something that's an artifact that looks like a tumor, they might go and cut the brain open and uh-oh, they might find nothing. Then you're in big trouble and they'll blame this on you. So, all right, so what do we have here? This is a cut, sagittal cut through the brain, right at the air tissue interface, and right here at the pituitary gland. Okay, this is actually a very nice picture. You can even see the sinuses. And amazingly, this is not a spin echo scan. This is a gradient echo scan. Usually you don't see anything here. And you can see the boundary here along the tissue-air interface, and here as well. This is really a very good picture. So how do we get to that picture? Maybe it's not so easy. So when we do gradient echo imaging, we have a number of variables available to us. So we have to apply an RF pulse repeatedly to do my phase encoding, right? So if we have the spins like this, I tip the spins, I measure it. And I wait till the signal disappears, the signal regrows, I tip the spins, I measure it again. And I do that maybe 200 and some times, right? So during that process, the signal builds up according to this formula, where E1 is e to the minus TR over T1. And the usual formula for spin echo is just rho naught 1 minus E1 times the T2 star decay term. But for the fast imaging for gradient echo, it's 1 minus E1 divided by 1 minus E1 cos theta. So when you look at this formula, if you're really good at mathematics, maybe you're comfortable with this. But if mathematics isn't your specialty, you can still understand this formula very nicely. And so next thing to learn as a student and as a teacher, if you're going to teach in the future, is how can you teach somebody what's happening here? Don't expect them to understand all the mathematics, whether it's Fourier transform or whether it's an integral equation or this formula. Instead, take a look at this function and ask yourself what happens for this function. This function must have a minimum, two minimum, and a maximum. Now how do you know that? It's very simple. If theta goes to 0, you have no signal, right? If I don't tip this at all, I have no transverse component. If I tip it 90 degrees, and I run my experiment very quickly, I also have no signal, because I don't give it time to grow back up. So clearly there must be a maximum. See, I didn't even need any tough mathematics to figure that out. If you want to find the maximum, how do you do it? You take the derivative of rho of theta with respect to theta, set the derivative equal to 0, and you can now find that the maximum will be right here. But I didn't need to do that to understand what's happening, right? Okay, so when I have theta 90 degrees, cosine of theta is 0. Good. So 1 minus E1 becomes just TR over T1, when TR is very small, right? E to the x is 1 plus x. So that's simple. And if TR over T1 goes to 0, I have 0. Okay, so this angle where you get the peak signal is called the Ernst angle. So now a practical question to ask you is, what represents a small angle in this experiment? So do you think 20 degrees is a small angle? So anybody, is 20 degrees a small angle? Certainly smaller than 90, right? It's a lot smaller than 180. But what does it mean to be small? Small flip angle, you might think, means that there's not much signal left. But at 20 degrees, there's a lot of signal left, right? So small flip angle means small relative to the Ernst angle. So if you're going to run an experiment on the magnet, and you run with the TR 20 milliseconds, and someone says, okay, I'm going to run a small flip angle, and they run 20 milliseconds, they're wrong. 20 milliseconds with 20-degree flip angle is a T1 weighted image. It's not small at all. So you have to go much less than the Ernst angle to have a small flip angle effect. So let's take a look at that. So here's my normal experiment. TR 20 milliseconds, 20-degree flip angle. You see the very nice T1 weighted contrast? The CSF is dark. The gray matter is darker than the white matter. And why is that? Because white matter has short T1, and this is a T1 weighted experiment. So 20 degrees is a very big flip angle. Now let's lower it from 20 to 10, still T1 weighted a little bit, down to 5 degrees. Notice the CSF is now getting signal, and the contrast has inverted between gray matter and white matter. And at 2 degrees, oh my heavens, look, CSF has got tons of signal. So why is that? Why, when I go down to almost 2 degrees, does the CSF now have the dominant signal? Because the only thing left is spin density. And CSF is 100% water. The gray matter is 80% water, and the white matter is only 65% water. So lo and behold, you can now create a spin density weighted image using low flip angles. Now, why is this simple exercise so important? Chapter 18 in the Green Book, just the first 2 sections. So you're going to get in a 7T magnet. in MR, even at low fields, with these implants, and they have come out very bad. They actually have been significantly hurt mentally, because what happens is heat, power got deposited by the metal, burned the brain tissue, and I think there's now evidence that 2 or 3 people have been seriously hurt this way. Why? Because these people didn't know what they were doing. They thought small flip angle. Maybe not small flip angle. If you get enough power deposited, you will burn your tissue. So if I drop my flip angle from 20 to 2 degrees, how much do I change the RF power deposited into the body? So B1 goes to 1/10 of B1. How does the power depend in MR? So you should all know this, right? If you do MR, you should know the power deposition. It depends on B1 squared, which means I have 100 times less power deposition at this low flip angle. So if you were going to scan me at 7 Tesla, and I was worried that you might be heating me up, there's only one scan I would let you do on me, that scan. And this scan would be good enough that if you were trying to find a tumor, you could find the tumor with this scan. So very important to understand the fundamentals of whatever you do. I just use this as one example. So let's go back to this picture. This is what the data would look like if you ran the same sequence with a bandwidth of 110 hertz per pixel. Now look at the signal to noise in the gray matter and white matter compared to this picture with a very high bandwidth. You see this is much better signal to noise. So sometimes the doctor is going to run a low bandwidth if he wants to see in the middle of the brain. Okay, that's all right. That's probably safe. But if his interest is the pituitary, and he were to use this image, he would go, oh, this guy, he has very tiny pituitary. Must be a problem. Shrinking pituitary. Of course, it's just a bad picture, right? Because in that part of the brain, you have such a big field change between the brain and the air. It completely ruins the picture. So if I go to high bandwidth, I have a much nicer picture here. And now I can start to see the pituitary. Okay? So why did I go from low bandwidth to high bandwidth? What's the advantage of going to a high bandwidth? Anybody know? So that means your read gradient amplitude is getting higher and higher, right? So let's say you have a background gradient caused by the air tissue interface. Let's call that gradient G prime. And let's call the read gradient G. If G and G prime are on the same order, you will cause a stretching or a shrinking of the tissue in the brain, just like you see here. You see I have all the signal loss here, right? So what do you want to do? You want to make G much bigger than G prime. So the bigger it gets, that means that the importance of G prime becomes less and less. Okay, so you have to use a very big gradient. So I do a good job. This is not a perfect job, by the way, but it's a good job. I would still not want to draw any conclusions from this picture. So what else is bad about this picture compared to this one? What's different here in this part of the brain? Anybody? You can see right away. Somebody want to tell me? Somebody has to be brave. Try home. What's the difference between the tissue here and here? Can you tell me? What's your impression?
Of course, the red one is more clearer.
Well, it looks like you can see things better, but what else about this picture?
It's edgy.
Sharper? True. Still one more thing. A bad thing about it.
Actually, the white line, the white line.
No, this is a little unfair because the window level setting is not as good to make the contrast look good. The signal to noise here is much higher than the signal to noise here. So you notice this looks kind of grainy, a little bit noisy. So the higher you make your bandwidth, the noisier and noisier the picture will be. So of course, if you have to make your bandwidth too high, say you made it 1,000, this picture would just almost disappear in contrast. You wouldn't see anything anymore. So you have to, unfortunately, life is a trade-off, right? Heisenberg's uncertainty principle. You give a little bit here, you lose a little bit there. So high bandwidth means low signal to noise. Okay, well that's too bad. So let's see if there's another way. How can we use our understanding of MR to make these images better? Yet again. Well, first, to understand what's happening, we need to look at the physics, the engineering, and the mathematics behind what's happening here. So this air-tissue interface creates this gradient G prime. And this gradient G prime is on all the time. But normally when we design an MR experiment, so we tip the spins and then we turn the gradient on, we reverse its polarity, maybe we turn it on again for a second echo, we change the gradient. So we have control over it. But we don't have control over the gradient that's inside your brain already. And that's this G prime term. So here's the gradient G for the read, and here's G prime. Now, how do we create an echo? We turn a gradient on till it develops some area A. We reverse the gradient to get an echo. So remember what we're doing here is we tip the spins, we turn the gradient on, they run away like this. If I reverse the gradient, they all run back together again, right? Okay, that's simple. So this is where my echo should be. But when I leave this gradient on, look what happens. Even if it's a very tiny gradient, the area underneath this gradient is getting bigger and bigger and bigger the longer that gradient is on. So the echo won't appear here. The echo will appear here. And if you wait too long, or if G prime is too big, the echo will actually go outside of your sampling window. Okay, if the echo goes outside your sampling window, there's no signal. So it doesn't matter how big you make the gradient. You will never correct the problem. So you have to start thinking, how can I fix this problem? There's only two ways to fix this problem. The first way is quite interesting. What if I just sample the gradient longer? If I sample the gradient longer, even if it goes outside the window, I can put it back in the window again. So what does it mean to sample the gradient longer? It means that I collect the data with higher k-space, and therefore better resolution. Now, how can we understand that? Why does better resolution make a difference here? So shifting the echo outside the sampling window is the same as this simple idea. So here's where the mathematician will tell you one thing, but the engineer will tell you another. So the engineer is going to think about this a little more from a visual perspective. The mathematician just does things. That's a Gedanken experiment. So I have all these spins. If the magnetic field is very bad, so all the spins run around a unit circle equally, what's the total signal? So I have a vector here and a vector here. And everywhere I go, I have a counteracting vector, right? So the total signal is 0, right? Now, what if I take that voxel and cut it in half? Well, now the spins don't go from minus pi to pi. They only go from minus pi by 2 to pi by 2, right? And if I add these guys up, guess what? I get 2/3 of my signal. I don't lose it all. So, from a simple understanding point of view, the better the resolution, the less phase dispersion across a voxel. Less phase dispersion, the better your signal. So now you can understand this from 3 different perspectives. From a Fourier perspective, from a sampling perspective, and from a resolution perspective. So the answer to the question then is, do higher resolution. Higher resolution will bring that signal back to you again. So another way to do this, sorry, let me go back here. Another way to do this would be, don't wait so long. Move this back here. So the area under this G prime is not so big, right? So the shorter echo time is another way to bring that back into the sampling window. So 2 ways to do that. Okay, so now let's look at this again. So here we have a reasonably good resolution. for what I'm willing to take that time for. And I have a high, so I really want to keep the scan time short if possible. On the other hand, I don't want to make any mistakes in interpreting the data. So let me show you an argument here why high resolution, roughly by a factor of 2, better than what people do today, can avoid a lot of problems. So maybe you all know what Gibbs ringing is. Gibbs ringing is when you try to take a boxcar function, so something that just looks like that, and you try to replicate it using harmonics. So those of you who like listening to music, you will understand this already. Those of you who do MR, you should understand that you can never create that perfect box, not with a Fourier transform, because it's made of sines and cosines, right? So what you get is you get a little dip here and a little peak here, and then it levels out at that edge. That's called Gibbs ringing. Well, it turns out that Gibbs ringing is present always. It doesn't matter what resolution you run. It never goes away. It shrinks in terms of its dimension, but it is pixel invariant. So you will always have plus or minus 9% mistake in what you do. So if you were to collect a very high resolution, and remember the ringing does this, it goes up and then down and then up and like this. So if I can do high resolution and then collapse back the data, so I take this point and average them, I can reduce a lot of that, right? That's how people get rid of Gibbs ringing. They filter the data. So in this case, what we did was to collect very high resolution of the gray matter, white matter, looking for the hippocampus. High resolution also lets you reformat the data in any orientation you want. And then we filtered the data. So you see that the contrast here is better than here. But when we filtered the data, we did something special. We filtered the data in the same matrix that you started with. So if you were to collect a lower resolution by a factor of 2, you would have a 256 image instead of a 512 image. So instead, what you want to do is a Hanning-like filter where you take 4 pixels in the original image and you average them. And then you move 1 pixel and you do 4 pixels and average them again. And you do this, what we call a sliding window filter. By doing that, you maintain the matrix size of the original image. And that actually has some magic properties. It gets rid of most of Gibbs ringing, and it actually still highlights small vessels. So if you were to collect the lower resolution image, you would actually get 30% less response from the small vessels than you do by using this trick. So in this perspective, the Fourier theory is not linear. In other words, if you filter the data, you destroy the linearity of the Fourier transform because it's a nonlinear process. So a lot of little tricks that you can do to just make things better and better. All right, so you know what? I have another hour to go. So I'm wondering if we should just have a second talk. Or you know what I can do? How about we do this then? I will stop telling all these stories. Do we have half an hour? Okay, I won't tell you so many stories, but I will leave the slides with somebody. Here you can put them on one of your websites, okay? And those of you who want to look at some of these in more detail, you can. So I'll try not to go through too much detail here. So what we did is we took all of these basic concepts I've been telling you about, the high resolution, the susceptibility effects, and we realized that we could enhance the presence of small structures that have high susceptibility. And this is how we came up with this concept called susceptibility-weighted imaging, which lets us get very high resolution images of the veins in the brain. Now, for 100 years, doctors have focused on arteries. Because if you can't get the blood into the brain, you're in big trouble, right? You won't get oxygen delivered to the tissue. So mostly the doctors focus on the carotid arteries. And if the carotid arteries get narrow, this is a bad thing. But they really miss the boat. Because the other 50% of the blood vessels are the veins. And if you can't get the blood out, you're just as dead as if you can't get the blood in. So, but the veins are much more interesting than the arteries. Because the veins tell you if the brain is working. That's how functional brain imaging works. but that's how many other diseases are also affected, as we'll see here in a few of these slides. The venous system is by far the most interesting part, in my opinion. But it's been a big battle for me to convince clinical people they should be paying more attention to the veins. Now there was a gentleman, his name is George Salomon, and he's been publishing this type of work for almost 50 years. He's done about 500 cadaver brains. And when I sent him this picture, 10 minutes later I got this back from him. And he says, this is wonderful. He says, I don't have to do any more cadaver brains. Because his whole job for 50 years was to inject a dye inside of these cadaver brains to try to image the blood vessels of the brain. So we don't have to do that anymore. And I also promise my students I will never send them to George Salomon. Because I definitely don't want him fooling around with it, okay? So definitely you can get your scan at my place. All right, so what can we use this sensitivity to iron for? Well, one of the most important applications is to something called traumatic brain injury. Traumatic brain injury in the United States, there are 2 million people a year affected by hurting their head. I wonder how many in China. I would assume at least as many, right? Maybe 10 million people. So traumatic brain injury is extremely important. And this is a CT scan of somebody who had traumatic brain injury. And what does it show you? It shows you one big bleed here, and that's about it. Generally, CT doesn't show you a lot of things. This is the conventional type of gradient echo scan that the doctors use, and it shows you much more. And this is the SWI scan that highlights on the changes in iron content in the tissue. And in fact, many times you can see single pixel effects. Those single pixel effects can actually come from a bleed of a vessel no thicker than my hair, 50 microns in size. In fact, MR is so sensitive that today people use iron tag stem cells to actually image the motion of stem cells inside of animals, for example, when they're trying to study the role of stem cells in fixing your brain or fixing the tissue. So it shows that MR is incredibly sensitive to these inclusions. Okay, well this is kind of for fun. If we know we can image iron, that means we can also study iron in an area that's really hard to get at. If you're a mother and you're carrying a baby, you don't want your fetus to have a CT scan because it's got radiation. So if you could do this with MR, it would be great, right? And you want to make sure that the fetus doesn't have traumatic brain injury or some other type of brain injury like this. And sometimes, though, a fetus can have thrombosis. They can have hemorrhage. They can have a vein of Galen malformation or coagulopathy. They all change the iron content in the baby's brain. So we have now started to do the same type of SWI. So here's the baby inside the mother. And now we can take this picture throughout the whole head of the baby, right? And here's another picture where you can see the baby here, head down. We take many, many slices like this through the mother. This takes about maybe 3 seconds for each slice. So if we cover all these slices, it takes 3 minutes. In 3 minutes, I can go through the mother and the baby like this. And we just did this a few months ago. So when I was here a year ago, I didn't have this data. And to my surprise, we were really not looking for the mother particularly. We were not looking for the baby. We actually wanted to study the placenta. The placenta basically provides all the nutrients to the baby. It has all the blood vessels that then go into the baby. The mother's blood vessels come into the placenta like this, and then on the inside, the chorionic vessels go to the baby, eventually through the umbilical cord. So we then created this picture, and the student, he was a little bit sneaky. He said, okay, Dr. Haacke, well, we've evaluated the data, and I said, oh, that's a really good picture of the mother's heart. And he says, no, that's not the mother's heart. That's the fetus heart. So it's really quite amazing. In that 3 minutes, we're able to get a picture of all the great vessels of the baby's heart. And more than that, if we now start looking at what we first wanted to do, these are the blood vessels in the placenta. So inside is the baby, outside is the mother. And this is extremely important because they didn't have the right blood supply to the placenta. So if you can study the blood supply, you can maybe predict whether the baby will be born early or not. You can try to make sure that everything is healthy for that baby. All right, so switching gears a little bit away from the simple applications. So we talked a little bit about gradient echo imaging. We've talked about SWI. But one thing I didn't really focus on yet is the fact that in MR you have two types of pictures. You have a magnitude image and you have a phase image. And if we merge these together, we can collect SWI data. If we use the phase data, we can create something called a quantitative susceptibility map. And from this, we can then create some improved algorithms for QSM, and we can create what we call true SWI instead of the original SWI. So to show you, remember I gave you that story about how we filtered the phase data, and all of a sudden we found something we never expected. So this is the type of data people looked at for 20 years. And then we started to do a high-pass filter of that data. And the more we high-pass filtered the data, the more we could get rid of all of this air-tissue interface, everything coming from the magnet, and look what we ended up with. Well, when we saw this picture, we were really very excited. We thought, this is amazing. Look at the detail. In principle, maybe we would have seen nothing. You know, if there's no iron in the brain, it just would have been flat. But the exciting part was, look, you can see the globus pallidus. Why can you see the globus pallidus? Because it has more iron than almost any other part of the body. So we realized we could now image the iron here. So in this sense, phase imaging is like super high resolution MR spectroscopy. It's a pixel by pixel spectroscopy map. It's a frequency map. So if you had metabolites in any structure, by the way, if anybody is doing NMR in this group, or if you're doing high field spectroscopic imaging, if you do high enough resolution so your metabolites sit within one voxel, you can do super high resolution spectroscopy. You're looking at it right here. So there are some nice tricks that the MR imaging can help improve high field spectroscopy. In fact, the same tricks that I showed you in the pituitary can be used at high field chemical shift imaging in NMR. And you can then create a perfect spectrum independent of any bad field. Most NMR people do not realize this, but actually it's quite possible. So when you do this high-pass filter, look at the type of image you get. So I go a little higher up into the brain, and all of a sudden I see the gray matter, white matter very strongly differentiated. For those people who do functional brain imaging, this is a very interesting area. This is the motor cortex. You can see the omega sign here beautifully. So the motor cortex is very easy to find. Now, about 15 years ago, a group in St. Jude's Children's Hospital in Memphis, Tennessee, they actually did a study here and showed that you could see more iron in the posterior part of the brain and less iron in the anterior part of the brain. And they showed that the gray matter actually has a longer T1 in the frontal part of the brain and a shorter T1 in the posterior part. And why is that? Well, because iron also acts as an electron paramagnetic agent and can reduce T1 of the tissue. So not only does it create a susceptibility effect, it changes the tissue properties as well. Now this is an example at 7T, and again it just shows you very nicely the small vessels you can see. So let's take a look at the detail here and why it's so complicated. Why did it take people so long to really discover this? Well, it turns out that the phase is proportional to the local geometry magnetic field, it's proportional to chemical shift, it's proportional to the global geometry, and it's proportional to any changes in your magnet. All of these things together, we have to eliminate the ones we don't want. And what we really want to see are the local geometry ones. So if I do a high-pass filter, I can get rid of the things I don't want and just end up with the small structures. So that's what we did in that previous picture. So now we need to go to the next question. So you might say, well, isn't the phase image good enough? Why do I really need to go and do a magnetic source image? I used phase for 20 years on SWI, very successfully. Well, the reason is if you want to quantify things independent of geometry, you need to just have a source. So let me show you how this works. And if you have the source, you can do oxygen saturation, iron concentration, and calcium measurements. Sorry, I'm going to skip this. So if you put either a sphere or a cylinder inside a magnetic field, it creates this dipole effect. So you can see that the phase information, if this is my vein, the phase information is everywhere around the vein. Which means if I try to use that phase information outside, it has nothing to do with the vein at all. So if this is a microbleed, and I'm using the phase here, it has nothing to do with where the microbleed is. So what I want to do is to create a magnetic source image that represents the object itself. And then I can use that information. So the question is, how do we do that? How do we get rid of all of this effect? And just to show you the problem it causes, when we do SWI, the phase of that vein changes when it goes from being perpendicular to the field to parallel to the field. And therefore, my algorithms in SWI don't work because they depend on negative phase. So if we look at a first-order expansion of Maxwell's equations, you do the Fourier transform of Maxwell's equations, you can actually show that the local magnetic field is equal to this function. It's the Fourier transform of the source of the object multiplied by the Green's function, inverse Fourier transform, times the main magnetic field. And this Green's function looks like this 1/3 minus kz squared over k squared. And if you do the forward model using this dipole approximation, you can predict what that phase looks like. So the question is, can we go backwards? So, you know, if you have a forward transform, does there exist an inverse transform? Well, you might already guess that because this is 1/3 minus, when 1/3 equals kz squared over k squared, I will have 0. It's going to be tough, right? Because if I can rewrite that formula now, the source is equal to the inverse transform times the inverse Green's function times the Fourier transform of phi of r, then this guy is going to have zeros. See, he's going to have 0 when kx squared plus ky squared equals 2kz squared. So is the problem solvable? Well, the answer is theoretically no. But practically, if the area around which that singularity occurs does not play a big role in the reconstruction, maybe we can just make that 0, or we can regularize that. And maybe I'll still get a decent reconstruction out of it. And I can say that nature was very kind. I mean, in North America, we would say God was kind. Maybe in China, you would say Buddha was kind. But in any case, nature has been very kind to give us this possibility that it actually does a pretty good job reconstructing that source. Except there are still some artifacts outside. Not perfect, but not bad. And if we use this technology, we can take the phase images that we had in the brain and turn them directly into source images. So you see this ugly dipole here turns into a nice cross-section of a vein. So this is really exciting that we can do this. And I'm going to skip some of the complications associated with this for now. We've developed, and there are many people developing wonderful approaches to try to solve this problem. We developed one approach where we did something very simple. We took this dipole image, we did the inversion, we have these artifacts, and we took, in fact, this is the first one, we took this image here and we said, you know what, the artifact is not that bad. Maybe it's less than 10% of the source itself. So we thresholded that object and said, let's just keep everything above 10%. And in that case, I have a good estimate of the object. It's not perfect. And then what I'm going to do is do the forward transform. And remember, when I do the forward transform, there are no zeros. So the forward transform is basically perfect, as close as dipole can be. So if we do the forward transform, I can now fill in the missing parts of k-space that I had to regularize before. So this is my way of regularizing the data. And if we do that, then the second time I reconstruct, I get this. The third time I reconstruct, I get this. And all of a sudden, we actually have very good reconstructions. So here's the iteration, and here's the difference between those iterations. All this streaking is basically removed, and in fact you can see that generally the signal to noise here looks much better because we removed most of that problem. The nice thing about this iterative approach is extremely fast. It doesn't matter if I'm doing 128 points, 256 points, or 1,024 points. It's very fast. But if you try to take any matrix algorithm that needs to calculate anything with SVD, or any type of matrix inversion, you're going to take days to do that type of reconstruction on large matrix sizes. Whereas this only takes seconds to do the reconstruction. So this is just an example of, again, the type of data you can get where you can image these vessels without any constraints on the system at all. Now, I have this challenge for Professor Lee, and so this is a challenge for you. Which one of these pictures is QSM? And which one of these pictures is phase? Can you tell me the difference?
The other one is the QSM.
Why is that? Why is that? Doesn't look like it has as good contrast, does it? Really, there's wonderful contrast here, isn't there? Can you tell me why?
But the edge is small.
Very good. So the edge here looks dark, right? And that's because the phase was dark there. So it's not as dark here. But it's pretty amazing, isn't it, that these two pictures look so much alike? Now, how is it that I was able to do that? And by the way, I didn't need any reconstruction here at all. So there's two things about this. Okay, this is just a maximum intensity projection over 5 slices. When you do maximum intensity projection, you remove almost all ambiguities associated with phase. However, you can't quantify it like you can quantify this. So this you can quantify in how many parts per billion field shift takes place. This, in theory, I could quantify, but it's much harder to do it. So again, it depends on your purpose. If your purpose is to quantify, you'll want that picture. But if your purpose is to just get a quick view of what's there, it's good enough. So it's kind of interesting, just the quality you can get out of that. By the way, I won't tell you, it's 50-50 so far. So you guessed the right one, but I've had maybe 4 out of the top world experts have tried, and it's 50-50 in what they guess, so it's quite interesting. So here's an application of QSM, and you can see the iron in the globus pallidus, you can see iron in the putamen, you can see iron in the midbrain. So now it's not just seeing the iron that's critical. If you sit at your computer, you put your cursor there, it will tell you the globus pallidus has 200 micrograms of iron per gram tissue. So why is that important? Let's go back to stem cells for a minute. Iron-tagged stem cells. So you want to know that if you've developed some new treatment for cancer, maybe you've developed some ligand or something that can tag part of the cancer, but you want to know if it's doing it or not. So you tag that with iron. And then you can see if the iron goes to the cancer or not. And if it does go, you know that this new drug you invented is working. But of course, it may only be a few cells that are able to measure or that you're able to see with this approach. So do we have the sensitivity to map out just a few cells with this? So we won't know until we do the signal-to-noise calculations, right? But practically speaking, we have pushed the limit of this technology today that we can see roughly 100 stem cells at high field. So at 7 Tesla on animal studies, we think we can now see 100 stem cells. That's really pretty fantastic because they usually inject millions of stem cells into the tissue. So one of the goals of imaging humans is to be able to see, can we map out the migration of the stem cells? We've done it in animals, but not in humans yet, unfortunately. So that's where some of this technology could lead you in terms of new experiments. All right, let me skip ahead here. This is kind of interesting. This is an experiment from Ye Yongchuan, who was at the Chinese Academy of Sciences about 5 years ago in Beijing, and I was lucky enough to recruit him to Detroit. And he's done some wonderful work there, and this is an example of a scan that is pre-diamox and pre-caffeine. So this same idea is what I showed you a little while ago here, but there's clearly a big difference between the pre and post diamox. You notice that they get darker, and the pre and post caffeine, they get brighter. So let's understand what's happening here. We can now probe the function of the brain by using 2 cups of coffee. So this is the equivalent of somebody having 2 cups of coffee. And if we plot the susceptibility, the black line is post-coffee. Notice the susceptibility of the veins has gone up dramatically. Anybody know why that's the case? Why is drinking coffee making the susceptibility of your veins change? Who does fMRI here? Which of you does fMRI? Anybody?
Caffeine slow down CBF.
Very good. Slows down CBF. And if it slows down CBF, it means that the brain has taken out more oxygen, right? So there's more deoxyhemoglobin in the venous blood. And more deoxyhemoglobin means higher susceptibility. So sure enough, you can measure this very clearly. Maybe in the future, you could imagine using QSM as a way to do functional brain imaging. If you have very high resolution and you're looking for major veins as the source, then that might be possible. In the case of diamox, it does the opposite. Diamox increases blood flow, so it decreases the bold effect, and you can see that here. So another nice application maybe of QSM in the future. Now, I want to show you something else that's kind of interesting. I'll try to just finish 2 more things and I'll stop for today. But one of the problems in doing QSM is you need to get the phase accurately. And getting the phase accurately is a bit of a challenge. If you have 3-dimensional picture of the brain and the phase has aliased like this, people have developed some very nice algorithms for trying to unwrap the phase by looking at local information in 3 dimensions. It's a very complicated approach to do that. It's actually much easier if you can use an MR method to make this a pixel by pixel calculation, because then it's very quick. So if we were to take 2 echoes, say an echo time of 5.68 and an echo time of 8.25, both badly aliased, if I divide one of them by the other one, now it's only the difference that's important. So this is an effective echo of 2.58, and you can see now there's almost no aliasing. So if you design the MR experiment in a way that you can collect, say, for argument's sake, you collect the data twice, maybe once with TE8, maybe once with TE7, and you complex divide them, you get the equivalent of a TE1. So the question is, why didn't I just collect T1 millisecond? Because you can't. You don't have the gradient strength to be able to collect that short an echo time. So instead, you do this by a sneaky way and do this complex division. Well, now you have no need to unwrap the data at all anymore. So the current approaches for QSM, they basically take the brain, they take the phase, they strip outside the brain, so they just look at the brain itself, and then you do the inversion process. And if you do that, this is the type of susceptibility map you get in the lower part of the brain. It's pretty useless. It's not, this map is not meant to look at gray matter, white matter. This map is meant to look at the sinuses. And it just does a terrible job. Well, why is that? Well, let's think about it for a minute. 2 things. Above that blood vessel sits your skull. If you take the skull away, you can't measure the dipole effect of that superior sagittal sinus. You have only half the information. And the same is true for the sinuses here. If you take the rest of the brain away, You only have the phase that goes into the skull, sorry, into the brain, not the skull. So you threw away a lot of important phase information. So what we have done is not to throw away the outside of the brain. So first you have to ask yourself, why do people throw it away? Because the phase is terrible. It's a mess. There's huge artifacts in those areas. But not when you do this complex division trick. Every single pixel, even if it's a single point in the sinuses, is now properly defined in terms of its phase. So if you do that, look at the reconstruction you get. So now you see you can reconstruct the sinuses perfectly. Well, wait, isn't that interesting? There's no protons in the sinuses. They're just air. So you're now looking at a picture done by MR of something that has no signal. If I put this inside a gel in the magnet, I can now image this plastic. I actually don't image the plastic itself. I image the susceptibility of the plastic. So this picture we're looking at is actually a map, a three-dimensional map of the susceptibility of air. Of course, that should be uniform. And if you do a measurement here, lo and behold, we find 9.2 parts per million. So we know we have done a good job in terms of reconstructing this. And so here's an example of the different types of sinuses you can see. So the frontal sinuses, the maxillary sinuses, you can see the teeth. I'll show you that in a minute. You can see the ear canal. Now this is also very interesting because the ear canal is air, of course. So there may be many applications of this. By the way, you can also see bone. So again, if we can develop the technology at low field to image bone, you don't need CT anymore. Maybe we could even image bone cancers and all sorts of things like that by using low field instead of high field. Okay, here's an example in the teeth. The teeth now look black. So why do the teeth look black? The veins look bright on QSM. The air looks bright on QSM, but the teeth look black. Why is that? Black means negative susceptibility effect, because calcium is diamagnetic. The iron is paramagnetic. So calcium should be negative. Actually, that's also a very important application in MR, because if you do a normal T2 star image and you look at the magnitude image, if it's calcium, it will be zero signal. If it's blood, it will be zero signal. You can't tell the difference. Now, if you do QSM, of course, you can separate iron because it's paramagnetic from calcium, it's diamagnetic. And here you can see the measured change inside the teeth. In fact, this is a picture. I had just been to the dentist and I was telling my dentist about this, what we were doing. And he goes, oh, he says, you want some teeth? And I said, sure, as long as they're not mine. And he was kind enough to go into a drawer and he says, oh, I've kept all these different teeth. So he gave me a bunch of teeth to image. And one of them had a porcelain cap in the top here on this part. So we imaged this tooth in 3 dimensions. And this is the reconstruction. You can see that mostly the negative diamagnetic effect, except by the porcelain, which has much less diamagnetism. So in principle, you can now even image teeth. Now finally here, I want to show you something that's very exciting about this. So in QSM and in many of these other problems that I showed you at the beginning, we have to do a high-pass filter or sharp filtering or some type of filter to remove this unwanted phase, right? Actually, we don't anymore. If you have a good picture of the brain, we can just do a forward model. Now, what would the forward model of the brain do? So here we have the original phase pictures for a sagittal slice through the brain. Now, what we do is we go and take the whole brain and just create a duplicate of the brain itself without any air around it. And we just force the air to be 9.2 parts per million. And then we do the forward transform, because remember, the forward transform is perfect. No problems. So if I do the forward transform based on the MR picture itself, based on the magnitude of the MR picture itself, I predict the phase to look like this. So if I did a perfect job, if I take this minus this, I should get 0. Well, I don't do quite a perfect job. because I don't detect the brain absolutely perfectly. But you can see that most of that phase is now gone, and the inside of the brain is easily seen and requires no filtering. So, in principle, we're probably still going to have to do a tiny bit of filtering here, but the better we get at estimating what the brain looks like, I can now eliminate these problems. And remember the story I told you at the beginning was, what was a problem now becomes a new application? So, what was a problem has now turned out to have potential applications to image materials. Now, whoever thought that MR might not just have clinical applications, but might actually have applications in material science? How do you study computer chips today? You do this using X-rays. And so you have a whole special, very expensive environment called synchrotron radiation that can be created and used for this. Millions and millions of dollars to make this type of facility. Okay, forget it. Just stick it inside a magnet. Maybe we can image this at 7 Tesla with 10 micron resolution. Maybe I don't need X-rays anymore to do this. So this is something for you to think ahead. Where does the future lie for new applications here? So it's generally a pretty good fit. This is an example of the profile. It's not too bad here. It's not perfect. But generally, our reconstruction has created the right phase for this. And why is this all important in the end? Well, here you can see the inability to image the... And by the way, you don't want to take the oxygen saturation out of the artery. That's a bad idea. So what other way could you do this? Anybody? Use your imagination. Be crazy. Be flexible. This is where you have to overcome Zhu Liang's initial concern. You have to say, maybe it's possible to do the impossible. So nature won't do it for you. So what if instead I inject a contrast agent into the blood? And this contrast agent is an iron-based contrast agent. And it has just the right concentration so that it makes the susceptibility of the arteries the same as the veins. Of course, that will now double the susceptibility of the vein, but they'll each be different than the background tissue. So this is really quite amazing. Here's our early attempt at doing this. So this is the SWI image of a rat brain. It's very high resolution, 40 micron resolution. And I can see veins. If I do QSM, I can see the veins. And this is after injecting an iron-based contrast agent. Absolutely amazing. All the arteries that I could not see before, I can see them all now. So in principle, the potential is there now to image the microvasculature, not just of a rat brain, but of humans. Because there's one drug out there that's actually allowed to be used today. It's a drug used to treat anemia, mostly for women. So if you have iron shortage, they give you this drug, and it has iron in it. And it first goes into your blood, and then your body gets the rest of it. So at the beginning, when they give you this, I can do this image. And so now we can use this on humans safely. And that means we can start to study diseases like dementia. What's happening to the blood flow in your brain if you're getting dementia? We can look at stroke. We can look at Parkinson's disease. Any other disease like this now becomes possible to tackle because we thought of this approach. But we would never have thought of this approach if we weren't already thinking susceptibility. Now, people use this drug called pheromoxetol for 2 other reasons. They use it because it's a T2 agent. So they use it because it makes the blood dark. Okay, well, that's not why we're using it. And they use it because if it gets lower concentration, it's a T1 agent. So it's become quite popular today because it's a safer drug than gadolinium. Gadolinium can cause NSF. Gadolinium cannot be used in people who have kidney problems. But interestingly, pheromoxetol can be. So it's becoming a more popular agent today. So I think this also opens the door for some really great new studies. And I have my fingers crossed because as I'm talking to you, right now Wu Dongmei is running SWI on one of the Lao Shus from Nanjing. to see if she can actually duplicate this from one of their studies. So hopefully this will be another great direction that can be pursued here with your expertise. So I'll stop there. Thank you.
I just have a question. How long will the conscious stay in the body?
Boy, are we ever lucky in this case. Gadolinium disappears in a half-life of about 15 minutes. This iron takes days to go away. So, in a sense, it's really fantastic. People have used this to study women with breast cancer. And the problem is that if you get breast cancer, you also can get cancer in the lymph nodes. So the lymph nodes can take up this iron contrast. And so if they're healthy lymph nodes, they take the iron up. And you can see them. But if they're cancerous, they don't work. So they won't take it up. So you can scan somebody when you give them this drug. You can bring them back a day later, and you can scan them again because they still have some of this iron in their blood. It's really phenomenal. So it may be that was considered a terrible problem that way will now actually become a huge advantage for us to follow people over time.
Actually, I have a program. If this iron region was injected into human body, will the iron metabolism in the body will be affected?
Well, I think this is why they actually give that drug. They give it to women who have low iron content. So they want to increase their iron content for iron utilization. So it's actually an FDA-approved treatment for that. You mean for people who don't need it? So let's say you don't need more iron. So how does the body get rid of it? Well, like it gets rid of most things. You take too much vitamin C, your body will get rid of it. If you have too much iron, the liver, the reticuloendothelial cells of the liver will absorb that iron and take it out of the system. So usually, as long as you're not giving large amounts of iron, it won't have a toxic effect. Now, if you gave way too much iron, in theory, you could have a toxic effect. But FDA would never approve it in that case. In fact, I can tell you, for 30 years, people have tried to use iron agents, and FDA has refused almost every one of them for that reason. Only one agent. So it's a fairly low dose. Well, you've all been very kind, but you've also all been very quiet. So you have some questions? You understood everything I said? Well, anyways, as I said, let me put one more thing up here, but I don't know if it'll work this time. If you want to get hold of me, please feel free. Let's try this time. Oh, this is really bad. You guys don't have Gmail, do you? Okay. All right. You can contact me at this email. It's not showing again. You can contact me at this email if you have any questions. So if you don't ask them now, that's fine. Okay. Yes, they're too shy. All right. Now, guys,